Before data becomes a packet, a frame, or a stream of application data, it exists as raw physics. Digital data travels as varying electrical voltages pulsing through a physical copper medium. The OSI reference model isolates this interaction at its base, designating it as Layer 1, the physical layer. Layer 1 is exclusively concerned with the mechanical, electrical, and procedural aspects of signal transmission. It handles bits, represented here as zeros and ones, transmitted over the physical wire. The physical parameters defined at this level determine the behavior and the performance limits of the hardware connected to the network. In the early 1990s, local area networks transitioned from coaxial bus topologies to star-wired configurations. This centralization was facilitated by a single hardware component, the network hub. This is a 10-base-T hub. Technically, it is classified as a multiport repeater, a device that operates strictly at Layer 1. Its function is entirely non-selective. When a signal arrives on any port, the hub propagates that signal to every other active port on the device. A hub lacks the circuitry to inspect MAC addresses or interpret packet headers. It cannot distinguish a legitimate data frame from random electrical interference. Without the logic to route traffic, the hub creates a single electrical environment where every connected device is forced to compete for the same physical bandwidth. Transmitted binary data as voltage over copper wires introduces a basic physical conflict. As a signal travels, it suffers from attenuation. The inherent resistance of the copper wire and external noise cause the waveform to gradually flatten and lose its amplitude. On early 10-base-T networks, this degradation imposed a strict 100-meter limit on any single cable segment. Active hubs were designed to overcome this by acting as powered repeaters. They receive a weakened signal, restore its electrical integrity, and retransmit it at its original power. While this solves the distance problem, it joins the separate segments into a continuous electrical path. This architecture results in a single collision domain, where the total rated bandwidth of the hub is shared among all connected devices. In this shared environment, a network collision occurs whenever multiple devices attempt to transmit simultaneously. When two transmitters apply voltage to the same wire at once, the voltages overlap. This creates a distorted amplitude spike, garbling the signal so it can no longer be accurately sampled as binary data by the receiving network cards. To manage this, hub-based networks are restricted to half-duplex communication. In half-duplex, a network card can either send or receive data, but never both simultaneously. This restriction places an inherent ceiling on performance. As utilization increases, the shared 10 megabits of bandwidth become increasingly congested, leading to frequent delays. Because a hub cannot manage traffic, the connected hardware must use a decentralized algorithm to coordinate use of the wire. This coordination is handled by the network interface card, using a protocol known as CSMA-CD. The process begins with carrier sense. The NIC listens to the wire, measuring voltage to ensure the medium is idle before attempting to transmit. During transmission, the card monitors its own receive circuitry. If an incoming signal appears while it is still sending, it knows a collision has occurred. The NIC broadcasts a 32-bit jam signal, ensuring all devices in the domain recognize the event and discard the corrupted data. Then, devices enter a backoff state. Each transmitter chooses a randomized wait time before resending, preventing immediate recollision. This reactive cycle allows multiple nodes to share a single electrical wire without permanent communication failure. However, CSMA-CD's effectiveness is governed by the speed of signal propagation and strict timing windows. For 10 megabit Ethernet, the system relies on a slot time of 512 bit times, approximately 51.2 microseconds. A collision notification must travel across the network and back within that 51.2 microsecond window. If the network is too large, a late collision occurs. The transmitter finishes sending before hearing the collision, assumes success, and drops the data entirely. To prevent late collisions, designers followed the 5-4-3 rule. This restricted a single collision domain to 5 segments and 4 repeaters, with only 3 segments allowed to host end-user devices. The size of these early networks was limited not by software, but by the mathematical reality of propagation delays across the medium. By 1995, the industry shifted to 100 megabit fast Ethernet, encountering new interference challenges on standard copper cabling. The Manchester encoding used in 10 megabit systems was too inefficient for these speeds. At 100 megabits, it would have required frequencies that exceeded the emission limits for copper wires. Fast Ethernet solved this using a three-tier encoding called MLT3. On the left, Manchester encoding requires a transition for every bit. On the right, MLT3 cycles through 3 voltage levels. This process reduced the fundamental frequency of the signal to 31.25 MHz, allowing 100 megabit data to be transmitted over Category 5 cables with minimal signal degradation. Even with improved encoding, the half-duplex nature of the hub still caused performance to saturate at high speeds, forcing a change in the physical architecture. The move toward modern switching represented a transition from a shared electrical medium to a switched logical fabric. Unlike the hub, a Layer 2 switch uses application-specific integrated circuits to make forwarding decisions at wire speed. By reading source and destination MAC addresses, the switch performs micro-segmentation. It creates an isolated collision domain for every individual port on the device. Isolating the TX and RX paths removes the physical possibility of collisions, allowing for simultaneous full duplex communication and dedicated bandwidth per port. While the hub is functionally obsolete, its foundational constraints, like attenuation, the single collision domain, and propagation delay, remain the invisible physical laws that govern all modern high-performance networks.